x naught plus delta, for example, in the standard model, times x u of x1 plus delta squared u of x2. So this u here is the instantaneous utility function that I'm focusing most of my attention on. This big U is, here it is, it's today. You're trying to decide which plan you want to choose. And that big U is your utility function over the whole plan, all future periods. And so it captures all these different dimensions of, it captures, all these different dimensions, not just the instantaneous utility function, but also this alpha, which is anticipation, and this delta, which is, right? Does that make sense? It's the utility of the whole plan. That's right. Why are we just using a summation? Well, what's your best guess as to why we're using summation? Do you think it's because of psychological realism? No, it definitely is not. You could sort of rank mathematical functions in terms of their tractability or manageability, and linear functions are always the most tractable, right? Because they're just so easy to work with. So any dimension of linearity that we can maintain in our models without losing all credibility, we'll almost always try to get as many things linear as possible. Now, originally, in this model, the summation really does break these periods down into completely what we call additively separable periods, right? So there's really the utility that you get in period 1 really has no effect on you in period 0 at all, except that you know that you're going to be this person in period 1, so you care a little bit about it now. But it doesn't affect your utility here at all. Now, in this model here, we have relaxed that assumption of complete additive separability by allowing tomorrow's utility to show up in today's utility. But we're still summing these things up, so there's still a dimension of separability there that may not be hugely realistic, but we're just trying to keep it as simple as possible. If you choose to gain u naught, aren't you inherently giving up utility at u1? No, because, well, in the thing that I'm about to show you, yes, because I'm about to show you an example where you can only do something once. But this might be a plan where you get a kiss from your favorite movie star every period. You're not giving up anything. And you might be choosing between a plan which is get a kiss from your favorite movie star every period versus get 10 kisses from your favorite movie star every 10 days. And we can look at which of those you prefer. Okay? All right. So let's just assume that your favorite movie star is too busy for that 10 in one day or every 10 days thing, and it's just going to happen once. Much to their disappointment, I'm sure. So let's consider a one-time activity that generates some utility ut, and we're going to make this a pleasant activity. So ut is greater than 0. So this is not the electrical shock. The electrical shock would turn this whole model on its head, and that's fine. We'll see that in a minute. And it can be either done now or at any future period, right? So you are choosing when to do it, which is another way of saying you're choosing between a sort of infinite set of plans, and the first plan is do it now and never again. The second plan is wait one day and then never again, etc. From the perspective of t equals 0, doing the activity at some future time t, well, it doesn't have to be future, at any time t, now or later, gives you this much utility. So this is big U of doing it at some time t. So you're basically, we're taking that big summation from the last slide, and we're just taking out one term, right, which is the term from the period when you actually do it, because all the others are going to be zeros. Yeah, Yago. Sorry? Oh, my goodness, thank you. Woohoo! That's not supposed to be a 2, that's supposed to be a t. Thank you, Yago. Yeah, delta to the t times 1 plus t times alpha u of t. So we're just taking that term out of the summation, because you're only doing this once, and all the other terms are 0. Okay. There's a blank space there, in which I imagine I would have something to write, but I don't. So utility maximization, right? These plans are different. So the plan of doing it now is just plug a 0 in for t. The plan of doing it tomorrow is plug a 1 in for t, et cetera, et cetera. And so utility maximization tells us that the individual will prefer to do the activity when this term here, delta squared times, I did it again, that's supposed to be a t. Delta to the t times 1 plus t to the alpha is biggest, right? Because u of t isn't changing. The value of this kiss in instantaneous terms is not changing. There's this term here that's sort of an inflator-deflator term is what I'm calling it. And that thing is going to change over time, right? Get bigger and then smaller in most cases. Sometimes it's just going to get smaller right away. It'll always wind up getting small, right? What you see here is that as t gets bigger, delta to the t gets smaller, but t times alpha gets bigger. And basically what happens is that because delta to the t gets bigger faster than t to the alpha gets smaller, eventually the discounting is going to win out, but sometimes not right away, okay? So that maximum might be now or it might be later. And we want to get some intuition into how do impatience and discounting affect the optimal timing. Sorry, I think I meant to say something different. How do impatience and anticipation? Apologize. How do impatience and anticipation affect the optimal timing? Now, intuitively, what we think is that as delta gets smaller, which means the person becomes more impatient, they should prefer/tolerate less delay, right? I want this nice thing now because I'm a big-time discounter. And even to the extent that delta captures how fast anticipation fades out, you get the same intuitive effect, right? If anticipation fades out rapidly, because you just tend to not think about the future as hard when it's further out, you should still want the kiss sooner, because you're pushing it out into the future means the anticipation just fades out. As alpha gets bigger, which means the person is more sort of quote-unquote anticipatory, then they should prefer more delay. The more weight you put on anticipation, the more you should want to push this thing out. So you've got impatience pulling the kiss closer in time, you've got anticipation pushing it out. And which one wins is going to depend upon the strength of these two factors. So let's graph this inflator-deflator thing and see what we might learn about the timing of outcomes. Right, so this is a strategy we haven't used yet for getting insight into something. Rather than actually doing comparative statics and taking derivatives of this thing to see when it's biggest, let's just graph it and see when it's biggest. Okay? So here's a graph where I have t on the horizontal axis, going out to 16, whether they're days or years, doesn't matter to me. And on the vertical axis, what I have is delta to the t times 1 plus alpha t. Okay, that's my inflator-deflator thingy. And I fixed delta at 0.8, which is pretty small, but I did this in Excel, and I just tweaked around the different numbers until I got something that actually illustrated the point. So this is a person who's relatively impatient, 0.8, and I'm going to give them different degrees of anticipation. Now, I actually did choose alphas between 0 and 1, but you could go past 1 if you wanted and see what happens. Here's somebody with no anticipatory utility at all, and they're just a straight exponential discounter. That's an exponential curve, okay? And then what you see is that there's the maximum size of the inflator-deflator if they have a little bit of anticipation, and then it gets further out. Now, because this is discrete, you don't see, but it would be a little bit further out if this was continuous time. And so what you see is that holding impatience constant, the more weight they put on anticipation, the more they want to push this thing out. But they don't want to push it out infinitely because eventually that impatience kicks in. And eventually they're going to start wanting it sooner. Or rather, eventually they're going to start not wanting to push it out further. Okay? So, sorry, where's the... So you're saying that the reason this is true is because the discounting is exponential and the anticipation is linear. That's right. That's right. So we could have tweaked this model so that alpha is actually also exponential and gets bigger and bigger the further things are out in time, and then you might get a different result. Yeah, Pedro. Hold on. Bedroom's question is it true that if you have strong anticipation of something nice in the future that you will do less to make it actually happen? So hang on, I think I can get to that. Okay, here's the same graph with the same set of alphas, but with somebody who's a little bit more patient, delta of 0.9. Okay? So in this case, all of these, right, with no anticipation, they're still exponential. But all of these maximum points are now further out in the future. So it's still the case that the more anticipation they have, the more they want to delay it. But because they're more patient, they're actually, all of these numbers are further out in the future. They're willing to delay more. Because now that impatience is not undermining their fantasy utility to the same extent. And then if the activity was unpleasant, this would be, all of these graphs would be flipped upside down, right? Because then the sign on little ut would be negative. And the fact that this inflated, sorry, the graphs wouldn't be upside down, but the implication would be reversed. The fact that this is highest here would mean that's when the shock would hurt the most. And that's when you'd want to, the fact that this is highest would mean that that's when the shock hurts the least. That's when you would care least about the shock. And you'd want to find the point that's got the smallest deflator, right? Which is either going to be now or sometime way out in the infinite future. So you would either want to get the shock over with, or you would say, put it off as long as possible. And what we actually saw in the Lowenstein graph was that people want to get it out of the way. They don't want to put it off. And the further out you push it, the worse they feel about the shock. Okay, to Pedrum's point. No, not quite yet. So takeaways from this model: pleasant experiences, you want to delay somewhat to have time for anticipation, but not too much because of impatience, and also because delay weakens the anticipation. For unpleasant experiences, you either want to do it now to eliminate the anticipation, or to delay it as much as possible for discounting reasons and to weaken the anticipation. If I could push the shock 100 years, 50 years out, probably people would start saying, yeah, okay, fine, push it out 50 years. Not 10 years, because I'm going to spend 10 years worrying about it, but 50, that's fine, I won't worry about it. Okay. Is this optimal delay time consistent? Okay, with a pleasant activity, Pedro, no, it's not time consistent. Here is why. Each period, right, you can't, unless you can like sign a contract and say, I want that kiss 3 days from now, come 3 days from now, and not any other time, right? Unless you can commit to that. When it's tomorrow, you're still going to prefer a 3-day delay, and when it's the next day, you're still going to prefer a 3-day delay. And so you're basically, what you see is that the optimal thing to do would be to always convince yourself that you're going to go on vacation next summer and then never go. That would violate rational expectations. This is a place where this model breaks down a little bit, and we need to think harder to how to salvage rational expectations and still have, yeah, so there's a problem there. And, oh, it is what happens. Yeah, I know, people are always crazier than our craziest models. With the electric shock, not necessarily, right? So suppose that you're one of these people who would really like to put this off 14 years from now. Failing that, get it over with now, but please don't put it in the middle distance. Okay, the problem with that is, unless you can commit to doing it 14 years from now, if you wait 7 years, you would choose, in 7 years, doing it now is off the table, so now it's just choosing between 14 or 7. What am I saying? Right, if you wait 7 years, then this becomes 7 years, this is off the table, this becomes now, and this becomes 7 years from now. And so, okay, why is that not what I think it should be? Oh, right, you would have preferred to have had it. Right, thank you. I don't know other people didn't hear that. Basically, okay, I'm having a moment of embarrassed irritation because I can't figure out what I'm trying to say, and I'm trying to move on. As an exercise, write down the sequence. Well, let's just do it, okay? So currently your ranking is, I like 14 years from now best, I like now second best, and I like 7 years from now least, right? If I wait 7 years, if I say, okay, in that case, let's put it off 14 years, and then wait 7 years, now is off the 14's off the table, right? Because I only get to choose between these 3 time periods, and now there isn't anything left that's 14 years away. And so my preference now has become, do it now has become the 7 years, and the old 14 years is the new 7 years, and so I'll prefer to do it now, because putting it off 14 years is now off the table. No, this is, so 7 years from now is the new now. 7 years out, this, right, doing it now is the old, so this thing becomes now, in some sense, right? Right, and the 14 years becomes the 7 years, and putting it off 14 years is no longer available. And so you'll do it now instead of waiting 7 years, which means that you did it at the time you liked least. Okay, thank you. Okay, so much for that. I'm going to see how far we can get on references for information. Now, when you prefer to put off an electric shock or kiss may or may not be that economically relevant. I think that if you're putting off getting bad news, it becomes really relevant. And so we want to take this into a realm where we think there may be some more problematic economic implications, which is preferences for getting information about the probability of future outcomes. Okay? So in the standard model, a person in a non-strategic setting, non-strategic meaning that they're not playing a game with somebody else with incomplete information, should never reject free information. Why? Because there's a non-trivial well, even if it's trivial, there's some possibility that it could be useful for decision making. Excuse me. And even if not, then you can just ignore the information. The information alone neither increases or decreases utility because the person can just ignore it. So even if the information is useless, you shouldn't reject free information. You shouldn't, certainly shouldn't have any willingness to pay to not be told some piece of information because you can just ignore it if it's not helpful. Okay? That's because the only value of the information is what it tells you about outcomes. But in a model of anticipatory utility, the person can't necessarily ignore the information because it affects their beliefs, and they have preferences over beliefs as well as outcomes. So here's some evidence of this. There's a paper by Poton Kosegi on the non-required section of the B-Space site that cites all of these findings. Most people who are at risk for Huntington's disease, which is a pretty nasty disease, which people are genetically predisposed to. So if you're at risk because your parents have the gene, but you don't know whether or not you've got the gene, people in that category don't want to know. They don't want to know whether they've got the gene. Okay? Now that's crazy because if you find out, either there's something you can do about it, or even if there's nothing you can do about it, it shouldn't matter. It should only be weakly positive things to get information about because you might be able to take steps to do something about it. Like say, for example, don't have kids, or make sure that you put aside enough money so that your kids can take care of themselves after you die at age 40, whatever it is. But people prefer not to. 50% of the people tested for risk of colon cancer declined to get the results. The test's been done already. Do you want the results or not? I'm just handing them to you right here. No, I'd rather not have them. Don't show me what's in that envelope. I don't want to know. It's like not reading your student evaluations. Fear of bad news is also cited in patients unwilling to get routine health exams and follow up on suspicious symptoms. Huge literature on this. Okay, so let's look at an example of this. And we'll just get started on this for a few minutes, and then we'll finish it up next time. A model of HIV testing over 2 periods, 1 and 2. Okay, at period 2, which is the future, the person will either be with certainty HIV negative, with probability P, or, there's a probability P now that in the future they'll be HIV negative. When the future comes, they either will be or they won't be. But currently, there's a probability P that they'll be negative in the future, and a probability 1 minus P that they'll be positive in the future, and they don't know. Okay? The instantaneous utility they're going to get in period 2 is just some number u of minus and u of plus, right? So however you're going to feel about being either HIV negative or HIV positive, we're just going to postulate that some numbers exist. And at time 1, in addition to foreseeing these outcomes, they also get anticipatory utility, some f of p, based on their belief about p. Right? So this is where it's really about beliefs and not outcomes in the future. Okay? So now, if I believe there's no chance whatsoever, I mean, currently my probability of having HIV next year is exactly 0. Hooray, congratulations, healthy living. And so my f of p is based on my belief that it's not going to happen. Okay? To capture some psychological realism, we're assuming that u minus is bigger than u plus, right? HIV is a bad thing. And also that the first derivative of this f function is positive. In other words, the more likely HIV is, or the more likely you believe you are, the higher the probability you think that you're going to get HIV, the worse you feel now because you worry about it more, right? Okay, and then we're going to make some simplifying assumptions that there's no intertemporal discounting because it just gets in the way, that there's no treatment available at t equals 1, which means that the information is not of any use to you in terms of outcomes. The only impact of the information about whether or not you are going to have AIDS in the future, or what the probability of AIDS is just the belief utility, anticipatory utility. It has no instrumental utility whatsoever in terms of treatment, and also that the person has rational expectations that they know what P is even without getting a test. And then what we're going to look at is at t equals 1, will the person decide whether or not to get an HIV test, where prior to getting the test, if they decide to go and get it, there's a probability P that they'll get good news. Whoops, that's supposed to be f of 1, which means that they're not going to have it. And with probability 1 minus p, they'll get bad news, and they'll experience anticipatory utility f of 0, because now they know for sure that they are going to get AIDS. Okay? And we'll look at what happens next time. So, sorry, let me hold your attention for 1 second longer. I realize I just made a fairly significant strategic error, because there's a problem on the problem set, problem 2, that is about this. I think, given what we've done already, that you can look through this and then talk to your GSIs or come to office hours, etc. And I think you'll be able to make some headway on the problem set based on these slides. I apologize for not getting through them. So if you have questions, post to the forum, and I can explain what we have not gotten to yet, either in office hours or on the forum.